guys, nice to see you. So let us recall our previous discussion. Last time we introduced the concept of uh, light and considered the nature of light, which under so which two concepts of light we can uh, discuss in different situations. So if we are talking about some interference effects or diffraction effects, this phenomena which we still are going to discuss in our course in the near future, then obviously we need to deal with the wave nature of light, and then we represent light as electromagnetic wave with some frequency, wavelengths, and instantaneous magnitudes for electric field and magnetic field, which are changing over time and in distance. So this model is quantitatively supported by system of Maxwell equations, and within the system of equations, it's possible to describe behavior of light in either in free space or in different medium. However, in some cases, it is necessary to consider different nature of light, which is particle nature of light, and what an example we can give in order to what kind of phenomena requires us to consider light as a flux of particles. Electrical reflection. External photoelectric effect. Also, we consider it as a concept of internal photoelectric effect. Both require considering a flux of photons as model for light. And the main reason what is standing behind, who remembers, let's say why we cannot explain external photoelectric effect in the scope of the wave models of light.
Because if we consider it as a wave, then it would mean if we apply the right intensity, then it would eventually absorb, but it doesn't absorb.
There is some words which have connection to the reality, but the conversion are not structured properly yet.
This density of the wave should increase the kinetic energy of electrons that drop out from the surface of the metal.
So that is expectation from the wave theory. And what stands behind that? Why? Why you believe that increasing intensity should increase kinetic energy of photoelectrons?
Because intensity of the wave is directly proportional to the square of the electric field. Each electric field should
like provide more energy to electrons, which are delocalized within metal, for instance, and that is expected that they will gain more energy. Particularly will be kicked out. There is some work function, so that's a feature of the metal. They will perform this work in order to get out from the metal and be transferred, so-called, to vacuum level. But residual energy, which will be gain energy minus work function, will be expected to be higher if intensity increases. However, in reality, what was observed?
The increasing intensity don't lead to any increasing of kinetic energy of the electrons, but instead only increase amount of electrons.
Amount of kicked out electrons. And taking this into account, Einstein came up with an idea that if we represent light as a flux of photons with given energies in monochromatic light, with energy of each photon h nu plus constant times frequency, then increasing in light intensity will result only in increase of flux per unit time per unit area photons without changing their energy. So that fits very well with the experiment because we see that energy actually of photoelectrons doesn't change as we increase light intensity, but number of the kick out photoelectrons increases. So with this was introduced concept of like second time was introduced concept of particle nature of light because as you remember Newton was the pioneer with this idea to explain light as flux of particles, but of course it was on a different level of understanding because at that time of Newton he didn't operate with photons and didn't define the how we can calculate the energy of this. So with this behavior, dual nature behavior, we need to keep in mind that light can be treated in different ways under different circumstances. So today we continue with, I guess it will be quite short discussion for today. We're not going to introduce any difficult topics, but we need to introduce ray optics. So ray optics is the field of optics which considers light propagation along straight lines, and it continues to propagate along straight line in uniform medium over space and over time until it meets some interface with another medium with different optical properties. Then the trajectory of light rays deflects, or it reaches some region where the properties, optical properties of the medium start to change. So they either change as a function of position or as a function of so that's general definition, but we need to also clarify under which conditions we can actually use concepts of ray optics. So if we consider some obstacles, like geometric size of these obstacles, that can be characterized by D, which are much smaller or comparable to the wavelengths, so it's distance between these two maxima, to the wavelengths of incident electromagnetic wave. In our case, we are talking about light, so light that is usually considered in the visible spectral range, and you know now that which spectral range human eye can see. We are talking about wavelengths in nanometers.
880 to 760.
Something like that, plus minus. Yeah, of course, there could be some deviations, but on average, that is the range. So you see that the wavelength is very small when we're talking about light, when we're talking about electromagnetic waves, which can be detected by human eye. So in those cases when obstacles are smaller or comparable, we cannot apply concepts of ray optics because of diffraction interference effects which can be involved in this process. However, if the obstacle in front of the front line of the front of the electromagnetic wave will be much larger than the wavelengths, which is true for our everyday life experiences, then we can apply concepts of ray optics. So you can see that here we can neglect with all these modifications of the wave shape after passing this large obstacle, and we consider it just as a straight line, the ray of light, which is propagating in within the medium where it moves. So that is the critical moment requirement for applying concepts of ray optics. And any examples? What would you consider a good optical system where design of this optical system will be fully based on ray optics concepts?
Probably glass or mirrors.
So if we consider in general, that's actually true. Yes, if we are dealing with the building of optical images, then we follow these concepts of ray optics. But if we're talking about some optical systems equipment that's like microscope, telescope, eyeglasses, all these regular conventional optical systems, their aperture is much larger than the wavelengths of visible spectral range of electromagnetic waves, and that's why we just deal with ray optics concepts. So as I said at the beginning, these rays are traveling until in the straight direction, straight line, in uniform medium, until they reach some non-uniformities. A classical example of non-uniformity is when we have interface between two different materials. So interface is always a transition in terms of properties of whatever properties we are considering, either optical or electrical properties. And in this case, what can happen? So first option is reflection. When this ray of light hits the surface of the interface between two media and is reflected, the angle of reflection is equal to angle, like incident angle, so these two angles are equal. And what is also important, that the reflected light, like reflected ray, stays in the same plane with the incident ray. So they form like they stay in the same plane. If we have rough surface, so if we consider something like this, rough surface is called in that case when the non-uniformities on the surface of this interface is not ideal flat interface between two mediums, but non-uniformities are larger than the wavelengths. So if they are larger than the wavelengths, then it already has a dramatic effect on reflectance. And in this case, of course, we're not dealing with such concept as clearly defined reflected ray. We have reflection in all directions, so we don't see any clear reflected ray in case of a rough surface. So this should also be taken into account. Not always we get a clear reflected ray. That depends on the quality of surface treatment. By the way, do you know what are the methods to treat the surface of glass or any other materials to get it smooth and get it as close to ideal flat surface as possible? What could be the, let's say if we are talking about glass, how would you have some glass sample, let's say with such scenario. So you don't see any reflected ray because it's rough. So you get some raw piece of glass, and then you need to treat it in that way that you get a clear reflectance ray. How would you approach this task? So there are sequence of actions which have to be carried out, and usually you start from mechanical polishing. So there are powders with different diameter of particles. So you start obviously with powders with larger diameter of particles because you initially start with really rough surface. You drop some water, put this powder, and with another piece of glass, start to polish the surface. So this particle, they interact with the polishing surface and piece by piece detach this damaged surface. Then you subsequently reduce the uh, size, the diameter of these powder particles, continue polishing. So you will make it smoother and smoother with each step further. However, the last step, when you want to delete all residual minor non-uniformities on the surface, you need to chemically etch the surface of glass. Any ideas which have you heard, by the way, had here this during your curriculum, general chemistry, inorganic chemistry? No? Nobody of you? Interesting. In high school, that's true. So from high school, that's also possible that you know it from high school. Which acid can dilute glass, like etch glass, or any other metal oxides? There is HF. HF acid can dilute glass. Uh, well, who has seen this series Breaking Bad? Do you remember that moment when they were trying to get rid of body? So that's the acid which they used, and they messed up with the container because you should deal with plastic container, and then it all was dissolved. So technically, yes, bones can be dissolved also because they are minerals, so they are also. That's why HF is quite dangerous substance, so you need to be very careful. But that's an option when you do the final polishing, not of dead bodies, but of glass surfaces. Then you need to use HF for etching the surface, and that's the way how you get the quite high uniformity of the outer layer. So now there is reflection, but not all light is reflected from the interface. Part of the light, if we are talking about some incident light intensity, so we can split it in two components. We have reflected and refracted light. So refracted light is that light which actually goes into the material, like second material after this interface. And we also need to know how it actually behaves. So you can see here in this example that part of this incident light is going inside the second material. It is second time reflected, goes out, and comes back to the initial medium. So, because of the fact that there is a difference between speed of light in these two mediums, V1 and V2, this refracted ray of light is at different angle than the incident ray of light. So there is some theta 2, which is different. And if we're talking about air, this is like air, and this is glass. So this angle will be always smaller because V2 is smaller than V1. Again, what we need to remember that all of these three rays, incident, reflected, and refracted, they will also remain in the same plane. So they will not move in different directions with respect to this plane where the incident ray is traveling towards the interface. Obviously, if we consider different combination of medium, then we have glass and air. So now glass is the first medium and air is the second. So speed of light in air will be higher, and this angle theta 2 will be higher than the incident angle. So let us try to write down some aspects of this. So tell me, what is the parameter which defines how slower light is traveling in given medium is with respect to free space?
divided by G.
So if we consider like c speed of light in vacuum divided by v speed of light in some medium which we consider, so what it will be equal to? N, and how we call this N? Refractive index. So refractive index tells us how many times light in vacuum travels faster than light in given medium. And keep in mind that this is wavelength or frequency dependent parameter. So with this parameter, which is unique feature of the spectral distribution of refractive index, is a unique feature of material. So we can consider, let's say, at some fixed wavelengths, the refractive index values for different mediums. So for obviously for vacuum, it will be unity, and for air, it will be like n will be close to unity. So it's like 1.000 something, but usually it's considered unity. However, for different, let's say, solid state materials, we get already significantly larger values of n's. For instance, n glass will be something around 1.5, 1.52. And for instance, if we deal with diamond, that will be 2.42. Of course, this is just a given some fixed wavelength because n is a function of wavelengths. And the fact that we have much larger refractive index of for diamond than glass results in this very nice appearance of diamond because they get very high reflective. The larger difference between refractive indexes of air and substance, the higher will be reflectance coefficient. The higher will be ratio of light, which is reflected from the interface between these two materials. So obviously with diamond, much more light will be reflected from the interface with air, and that's why it looks like so sparkly. So now let us consider this refracted beam, refracted ray. So it travels with speed less than speed of light in vacuum. However, how can we represent speed of light of any electromagnetic or any other wave? So we can have a product of wavelengths and frequency. Product of wavelengths and frequency gives us the speed of electromagnetic wave or speed of light. So what do you think? What is changing between these two parameters when light is going from air to glass, waves or light waves? Okay, and what stands behind your suggestion?
So, light, as was discussed, is both a particle and a wave. And if you look from a perspective of the wave, when the medium changes, let's take an example of just sound, which is also a wave. When the medium changes, the frequency remains the same. So, for example, if I dive underwater and somebody talks to me outside of the water, I can still recognize the voice because it will have the same frequency.
Okay.
Similar is probably.
So that is based apparently on personal experience of diving underwater and hearing someone talking to you. But on top of that, from physical point of view, how you would support the statement?
Maybe because in the solid body, the distance between the atoms and the crystalline structure is more like denser, yes.
Well, the distance between atoms in glass or any other matter is much, like orders of magnitude smaller than the wavelength, and that doesn't make big impact. Besides like creating this in terms of polarization medium, uh, creating some opposition for electromagnetic wave to propagate through the medium. That's why actually we get slower speed of light in this medium. However, if we are talking about the change of wavelengths or frequency, so you're right, wavelength is changing, frequency remains the same, and a fundamental concept behind this is conservation of energy. Yes. So the thing is that energy of a photon is h nu. So if it goes from one medium to another, there is no amplification or attenuation. So energy should be conserved. Frequency remains the same, but wavelength is changing. So in this case, we can write that V1 in the medium number 1 will be lambda 1 times F, and V2 is equal to lambda 2 times F. Frequency is the same, however, lambda 1 is not equal to lambda 2. And the ratio lambda 1 over lambda 2 will be V1 to V2. That is C over N1 divided by C over N2, and that is N2 over N1. So we can write from here that lambda 1 times N1 is equal to lambda 2 times N2. So this product of wavelengths and refractive index actually doesn't change. But if we consider only wavelengths, then wavelengths changes. So actually it gets shorter when it goes from air to glass, for instance, because n is larger than unity. So based on this concept, we can write the equation for refracted light, and that will be n1 times sinus theta 1, which is incident angle. That is equal to n2 sinus theta 2. So this is the law of refraction. So with this, you remember that reflected light incident angle is equal to reflected angle. When you deal with this ratio, you can also determine the refracted angle if you know incident angle and optical properties, in this case refractive indexes of the first and second medium. So we'll not go here in too much in details, but there is such a concept as full internal reflectance. So in that case, at some specific angle, when light is traveling from optically more dense material, that is optically more dense material, that means material with higher refractive index. So if you consider glass, for instance, and light is traveling from glass and wants to go out from glass to air with optically less dense material, then at some angle, which is called angle of total internal reflectance, all light will be reflected. There will be nothing going out from the interface to air. So there will be absent refracted refracted ray. So all light is reflected. It means it stays inside the optically dense medium. And this is the principle where optical guides or optical fiber is operating. So you know that nowadays, even in apartments, when like or houses, when you order service from providers of internet, they provide this optical fiber to even to apartments. However, obviously, like in between cities or between countries or continents, there are huge optical fiber network all over the world at the bottom of the ocean. So that is where the optical signals, which are created by some light emitting diodes with very high frequency, they are modulated in order to transmit with certain intervals. In order to transmit information, it's actually like considered zero and unity. If you have signal, it's unity. If you don't have zero, if you manage to transmit such pulses of light with certain frequencies, you can manage to transmit this information via optical fiber. It's designed in that way that the fiber material is very transparent for the wavelengths at which the light emitting diodes emit. Obviously, it has to be very transparent because communication happens at like insane distances, and you want to have minimum losses of this light intensity. And at the receiving side, you have some photodiodes which detect these light pulses, convert them into electric current pulses, and that's something what you can read with receiving equipment to transform into information. So pretty much that's the system of operation, and due to superposition of electromagnetic waves of light also, we can transfer through the same optical fiber like a lot of different signals from different users. So they do not overlap with each other, and that's really creates a broad band of transferring a lot of information per unit time through such optical fiber systems. Actually, the most efficient way to transfer information. So let us summarize our discussion for today. We introduced the concept of ray optics. We highlighted that ray optics concept can be applied only in that case when the size of the obstacle or optical system is much larger than the wavelength of light, and we know that visible spectral range is about 380, 770, 80 nanometers. So that's quite short distance between like the quite short wavelengths. So that's why it can be applied to such systems as binoculars, eyeglasses, all type of projectors, for instance. Also, they are using lenses to project the image on the white wall. So all these systems, they operate with the concept of ray optics. And in this case, light is considered to travel along straight line and change its trajectory only in that case when it meets some interface between two mediums with different optical properties, or when it reaches the region where the optical properties of the medium start to change either in space or in time. So when light ray reaches the interface between two mediums with different optical properties, two processes are happening. First of all, it's a reflection of light. So when incident and reflected ray are positioned at the same angle with respect to the normal, to the plane, to the interface, and also refracted light, which like part of light intensity goes into the second medium at some angle, which is smaller usually. If we are going from air to glass, for instance, that will be angle smaller than the incident angle because speed of light is slower, like less in the glass in comparison to air. So parameter which defines the ratio between speed of light in vacuum and in medium is the refractive index. Spectral distribution of refractive index is a unique feature of the material. So every material possesses its unique spectral distribution of refractive index. And when you need to do some calculations in terms of determining angles of refraction, for instance, you definitely need to know the wavelengths, because for given wavelengths you will have for different wavelengths you will have different refractive indexes. So if it's not specified the wavelength, then probably it's considered that it's not important within the given problem. However, if the wavelength is specified, then you need to be careful with this and be sure that you pick up the right value for refractive index, because it can change quite significantly within the spectral range. Okay, then thank you very much for attention. Have a good evening and also good spring break. I hope to see you alive and healthy after spring break. And we will continue with optical images in systems with lenses and mirrors. Have a good day.